Cool, thanks. Yeah, I'm realizing I might quickly regret the backboard first choice, but we'll see. But yeah, okay. So I want to tell you about a structural result for a type of object in a type of space. So there's two different things there to kind of introduce and motivate. Let me start by talking about the objects that the result will be about, namely quasiflats. So let me just start with some generalities about quasiflats in spaces. So definition. N quasiflats in a metric space X is just a quasi-isometric embedding of Rn into the space X. And okay, in general, these things can be pretty bad. So an example of so the name quasi-flat makes you think that it would be nice and flat, but an example of something that is a quasi-flat and doesn't look that flat is a logarithmic spiral. So if in the plane, if you take I guess I should start small, a spiral that's growing logarithmically, so these gaps are getting exponentially bigger, then that's a quasi-isometric embedding of a ray in the plane. And then if I stick another one of these on here going out as well, then I get a quasi-isometric embedding of R in the plane. Okay, and the fact that you can do that makes it seem like in general these things can be kind of disastrous. But the thing that's going on here is that I tried to put this is a one-dimensional quasi-flat into a two-dimensional, well, flat, but space. But really it's not, the problem's not that the target space is two-dimensional, it's that the target space is a two-dimensional flat. So to see that the problem isn't just the dimension of the target space. Think about, for example, if you look in Hn, in the hyperbolic n space, it's an n-dimensional space, but the Morse lemma tells you that every one-dimensional quasi-flat, i.e. quasi-geodesic, is Hausdorff close to some geodesic. And in hyperbolic spaces, there are no two-dimensional quasi-flats. So really, maybe the problem was that this wasn't a top-dimensional quasi-flat. Maybe the problem was because we were looking at a quasi-flat smaller than the biggest one there could be. And if I have a two quasi-flat in a space, I'll always be able to make this kind of example of bad one quasi-flat just by making it inside the two quasi-flat that I have. So any kind of rigidity statement about quasi-flats is going to have to be about the top dimensional or the biggest ones.
You make two quasi-flats in R3?
Well, you could do this times R. So depending on how, yeah. And probably you could do, you could probably do this times this and make a bad two quasi-flat in R4 that's even worse. But
Did you say exactly what you mean by a bad quasi-flat?
no, I did not. But yeah, I think this one's bad. Yeah. Yeah, I'm not going to tell you what a bad one is, but I'm going to tell you what some good ones are. And maybe a bad one is one that's not good. We live in a world of dichotomies. Okay, yeah. Right. Okay, so when you leave, so here there are no two quasi-flats. But if you leave hyperbolic spaces and go to other non-positively curved spaces, then you will have to deal with two quasi-flats. But maybe you can hope that, like I said, this was just a top-dimensional thing, and maybe in some other non-positively curved spaces you might have some control on quasi-flats. And there are various results in different contexts that tell you this kind of thing. So let me just list some results where people control the top dimensional quasi-flats in various contexts. So yeah, okay, so this is the point where it's bad. Okay, so yeah, quasi-flat theorems. So an early one is due to Kleiner and Lieb. And they showed that if you take a symmetric space or thick Euclidean building, locally compact, of rank R, then every R quasi-flat is contained in a finite union of flats. Okay, let me just write that down, and then we'll get to one where I can draw more of a picture in a second. In a rank R symmetric space, or locally compact thick Euclidean building, every R quasi-flat lies in a neighborhood of a finite union of flats. Where by flat, I mean isometrically embedded. All right. So this sort of thing isn't happening because here, this guy is not contained in a neighborhood of a finite union of actual straight lines. Yeah, you can think of it as being, there are some places where things change direction, but kind of most of the time it's looking pretty flat. Okay, so that's an early one of these kinds of theorems. Another one, a later one. Yeah, okay. This is kind of exceptional because these spaces are already very rigid. Okay, part of what they were proving here is a lot of rigidity for these things, but there's kind of a lot. The space is made out of R-dimensional flats, so it's kind of reasonable that you would wind up with something that's close to R-dimensional flats. Okay, another one. In fact, let me skip that one. Later, there's a result of Jinying Huang, who said that if X is an n-dimensional cat-0 cube complex, then every n quasi-flat in X is Hausdorff close to a finite union of orthants. And a difference here is that here it was just in a neighborhood, and now it's actually at finite Hausdorff distance. Every n quasi-flat is Hausdorff close. To a finite union of orthants. Okay, what's an orthant? An orthant is, so a 2-orthant is a quarter plane, like this. And a 3-orthant is a product of 3 rays, i.e. 1/8 space of R3, and so on. An n-dimensional orthant is a product of n rays. It's one of the corner bits of n-dimensional space. So in an n-dimensional cube complex, quasi-flats are close to unions of orthants. Why am I now talking about orthants and not about flats? Well, you cannot make this statement with flats. And here's an example. If you take a cyclic union of 5 orthants, like this, okay, hopefully that's still sort of visible. Here's the kind of middle bit of that. So this is 5 orthents glued around a point. There are no two-dimensional flats here. But this thing is quasi-isometric to the plane. Hopefully you can see or believe that that's quasi-isometric to the plane. So this whole thing is a two-dimensional quasi-flat, but there are no flats. So you really need to start talking about orthents when you want to work here. Orthents are the building blocks. And yeah, if you take two quasi-flats in a two-dimensional cube complex, it will look something like this. Maybe with more things glued at this point, maybe things will start branching out more over here. But there's finitely many, okay, no. There's finitely many of these orthents going on. Yeah, okay. Let me do two more. Yeah, or 1.5 more. Well, it's no, okay, it's two more. It's two more. Shouldn't criticize it like that. Two more. Okay, so another one is Bairstock, Hagen, and Sisto. They used this result of Huang to prove a quasi-flats theorem for mapping class groups, and more generally various hierarchically hyperbolic things. But let me just say there's a similar kind of result for mapping class groups. Yeah, there's a sensible notion of orthent, which really you can think about as being parts of Dane twist flats, and any top dimensional quasi-flat in the mapping class group is close to some union of orthents. The orthents are now not literal orthents like this, they're coarser things than over there, but broadly speaking, it's the same kind of result. And then one more, so these guys used Huang's result to prove this statement for mapping class groups, and then a year or two later, Brian Bowditch proved a stronger, more general result without relying on Huang's. It actually recovers Jingyin's theorem. Similar with more information. For coarse median spaces, which I'm not going to talk about at all. But suffice it to say that cube complexes are coarse median spaces, mapping class groups are coarse median spaces, and more things. Okay. Right, so that was a list of different places where you have these kinds of top dimensional quasi-flats are sort of rigid type result. Why would you want to prove such a thing? So let me give you two reasons, and you can choose which one you think is more compelling. So why bother? Okay, so one reason is that proving these kinds of results on quasi-flats is often closely linked with proving quasi-isometric rigidity results for these groups, and that's a quasi-isometric rigidity is something with kind of deep roots in geometric group theory. You're doing coarse stuff with groups, and so for example, so Klein-Alieb, their paper, they wanted to show that if you have a symmetric space for a building, then every quasi-isometry of it is at finite distance from an isometry. There's a really strong fact about isometries. They didn't actually use this. This was just a byproduct of what they had to do to prove that thing that falls out quite simply. But it's kind of intertwined with the argument. Huang, his results, so he was motivated by trying to prove quasi-isometric rigidity for right-angled Artin groups. And he actually does use this theorem in order to prove that if you have two right-angled Artin groups that are quasi-isometric and both have finite outer automorphism group, then they're actually isomorphic. So again, very strong statement where you get to go from quasi-isometries to a much more rigid thing. And yeah, these things, you can prove QI rigidity for mapping class groups using these kinds of statements. Bowditch has a quasi-isometric embedding rigidity type statement that he proves using these sorts of things. Okay, so that was a lot of words without writing anything. But one reason why you might want to have this kind of quasi-flats theorem is that, yeah, it's interrelated with proving quasi-isometric rigidity results. And a second reason is that as soon as you know some class of groups has some property, you can then turn that around and say, if I have a group that does not have that property, then it was not in that class. That's a pretty stupid way of saying it, but basically, once you have these quasi-flats theorems, that you can use that to find obstructions to a group being, say, co-compactly cubulated. So these kinds of theorems, yeah. So yeah, so you can use this kind of idea for some free bicyclic groups, for example. But yeah, these having statements like this can obstruct groups from being in certain classes. In a way where you're just looking at, you just need to know about the geometry of the group. You don't need to, which depending on who you are is easier or harder than looking at the algebra. Looking at you, Monica, can be used to obstruct a group from being, how do I finish this sentence? To obstruct a group from being what you thought it might be. Good. If you're taking notes and you look back at this in a week's time, you'll have no idea what that meant. So maybe you found a better way of writing it. Good. Okay, so right, so that was the sort of general thing about quasi-flats that I wanted to say. So are there questions about that before I switch to talking about hyperconvexity? Okay. All right, yeah, so now I'm going to talk about hyperconvex metric spaces. So let me just start right off with the definition, or one definition. A geodesic metric space is hyperconvex, also known as injective, if every family of pairwise intersecting balls has a point that lies in the total intersection. Give you a collection of balls, they intersect pairwise, there's a point that lives in all those balls. Yeah, it is pretty standard. There isn't a good reason why I've done that in this talk, actually. I thought there was going to be a good reason, and then I changed what I was going to do. The hyperconvex and injective were defined separately. Hyperconvex was defined to be this thing because this is a convexity property of balls. Injective is defined in, you can define injective in a more kind of categorical way, and it's called injective because then they're the injective objects in the category of metric spaces with one Lipschitz maps. Those things turn out to be equivalent. Not, but yeah. Yeah. For whatever reason, I chose to use hyperconvex in this talk, but it's possible I will forget because I do normally call them injective spaces. Yeah. I actually think hyperconvex is a better name because it's more evocative of this property, which I think is the easier property to think about than the other one. But yeah. Okay, let me give some examples of these things. So the first example would just be the real line. Balls are just intervals. If I take a collection of intervals that pairwise overlap, then there's a point that's in all of those intervals. And same idea, but more general, trees are hyperconvex. Okay. Another example, if I take the plane and I give it the L infinity metric, so the maximum of the two coordinate maximum metric, then balls in this metric look like squares parallel to the axes. So, and if I take a collection of squares like that that intersect pairwise, then there has to be a point in common. And the way you see that is you just, this square, you can just project to the factors. The fact that I'm using the maximum norm means this is just, you just do it one coordinate at a time. And that tells you that this thing's hyperconvex. And so that logic tells you that more generally, products of hyperconvex spaces with the L infinity metric. Okay, and let me do one more, which in a way you could think of as just kind of summing up the things I already said, is if you take a cat0 cube complex, normally when you're thinking of it as a cat0 space, you put the L2 metric on the cubes, but instead put the L infinity metric on those cubes, and that gives you an injective space, a hyperconvex space. Okay, those are some examples. I'll give you more in a minute. Let me first give a couple of non-examples. So one non-example is the circle, because I can just take, so that's a ball. That's a ball. And then that one's a ball. They intersect pairwise, but there's no point that lies in all three. Another example would be the plane, or the actual Euclidean plane, because I can take three pairwise tangent circles, and again, they intersect pairwise, but there's no point that lies in all three. So this tells you that it's quite sensitive to the metric that you choose, whether it's hyperconvex or not. Exactly, yeah, very badly so, because this picture is failing to be hyperconvex by whatever this distance is, but I could just make this picture bigger and make this fail as extremely badly. This picture happens at all scales, so they're extremely far from having a point in common. Okay. But it's still only three balls. Let me give one more example, which is going to be more challenging to draw. And I'm going to do R3 with the L1 metric. So R3 with the L1 metric, balls are octahedra. You've got distance this way, and this way. So let me draw a ball. Okay, and then it goes off to the back there. Okay, now I'm going to do another ball that intersected just on this line here. Let me make that red. Kind of red. Okay, so there's another ball down here. Okay. Now I'm going to do another one, and now it's going to get really hard to understand what's going on. And it intersects the first one along that, and intersects the second one along that. Maybe it should be a different color. So it goes like this. Sort of comprehensible. Okay, well now I won't draw the last one, but the last one, it intersects the first one along this, the second one along this, and the third one along this. Okay, those things formed a triangle, and that was a triangle that was a face of a ball. So you can believe that there is a ball that's there, and I'm going to put it, the one that's sort of up here. Okay, and so these three, the first three intersected pairwise. In fact, there was a point that was in all three of them. This one at the back here was in all three of those. And then the fourth one intersects each of these because they made it so it intersected along these lines. So these things intersect pairwise, but there isn't a point in common because the only point in common to the first three was at the back here. And the fourth one didn't hit that. So yeah, so here I found 4 balls that intersected pairwise but didn't completely intersect.
So R2 with the L1 works.
Yeah, that's funny because the ball in R2 with the L1 metric is a diamond, which is just a square turned by 45 degrees. So yeah, so it's a yeah. And there'll be something related to that in that.
The fact that you did 4 balls to make another example is it a dimension thing? Or?
I'm really glad you asked, Mark. Right? Because I'm about to tell you that it's not a dimension thing. Yeah, so funnily enough, well, okay, it's kind of a dimension thing, but well, okay, it's kind of a dimension thing. Yeah, so yeah, failure in 3 balls, failure in 3 balls, failure in 4 balls, and that is actually kind of a general phenomenon. So here's a result. Let X be a complete metric space of finite topological dimension. So it's kind of a dimension thing, but not really. And the theorem is going to be if every collection of 4 balls that intersect pairwise completely intersect, then that's enough to get hyperconvexity. So yeah, so if you only think about finite dimensional spaces, it's not a dimension phenomenon. Yeah, so this picture is really the worst picture that you can need to draw. Okay.
What do you mean by topological dimension?
Yeah. No, it's very reasonable. So in fact, do you know what asymptotic dimension is? Okay. No, because it doesn't matter. It means that if you take any point and look around it, you can cover a neighborhood of that point with opens such that you only use dimension plus, such that each point only lives in dimension plus 1 of them. So maybe you've seen this kind of brick picture tiling the plane. Okay, well, yeah, okay, I should draw it more like a brick. This means you can use this picture to show that the plane has topological dimension 2 because each point has a little neighborhood that only meets 3 of these guys. Yeah. If things aren't too degenerate, it's going to be what you assume the dimension is. Yeah. But it's a fair question. Okay, so right, so the list of examples that I gave so far was actually pretty restricted. And in fact, it was really just, I just told you that cat0 Q complexes. So that's, yeah, I mean, that's quite a lot of things, but yeah, there's a result that tells you that the class of hyperconvex spaces is actually really big. And I think this is just a cool theorem in its own right. This is an old result of Isbell. Which says that every metric space has a hyperconvex hull. Let me call this X, and then the hull is noted E of X. E is for envelope, hyperconvex envelope or injective envelope. It's a hyperconvex hull, i.e. a unique smallest hyperconvex space that it embeds in. Okay, so this gives you loads of different hyperconvex spaces. So let me tell you, so a couple of examples of hyperconvex hulls. So first one, the hull of 3 points is a tripod. This comes back to your observation, Francesco. This is, if you take the hull of Rn with the L1 metric, then that is R2 to the n minus 1 with an infinity metric. So in particular, when n is 2, it's just R2. Okay. But if you're skeptical, I maybe still didn't give you any new examples because maybe the hyperconvex hull was always just a big cube complex that contained the thing you started with somehow. But actually, there's a theorem of Lang which says that every hyperbolic space is coarsely dense in its injective hull. In other words, it's a subspace of its injective hull, its hyperconvex hull, and every point in the hyperconvex hull is within a uniform distance of the space, of the hyperbolic space. Okay, so in particular, this says that every hyperbolic group acts properly and co-boundedly on some hyperconvex space. And there are other examples of nice non-positively curved groups that have such actions, including Artin groups of FC type. So in particular, braid groups act on those things, even though we don't know if they act on cat0 spaces. Mapping class groups also act properly co-boundedly on hyperconvex spaces. And again, they're actually not cat0. And Eitel showed that there are uniform lattices in GLNR also act geometrically on these things. So there are lots of nice groups that act nicely on these things. Yeah. So a heuristic to keep in mind here is these are like cat0 spaces, but modeled on L infinity instead of on L2. That's why everywhere there were L infinities. In kind of in the same way that cat0 cube complexes are cat0 spaces, except modeled on L1. Okay. Right. Let me come back to Isbell's theorem. Oh, okay. Are there any questions about this before I say the next thing?
Is it right that sometimes when you take the hyperconvex hull, you can go to infinite topological dimension, so it can get nasty?
It can get nasty, yeah. In fact, if you take the hyperbolic plane, then its hyperconvex hull is at finite Hausdorff distance from it, but it has infinite topological dimension. Because topological dimension is a small scale thing, and so that can blow up without the kind of metric going off to infinity. Yeah. Yeah.
How about asymptotic dimension?
Well, okay. If the asymptotic dimension, so in these cases it doesn't change because it stays at finite distance, and but yeah, I don't know whether the asymptotic dimension can go to infinity from not being infinity. I suspect it maybe can, but I don't know. Yeah, I don't. Okay.
I mean, it can get arbitrarily larger.
Yeah, it can get arbitrarily larger. Yeah. But I didn't immediately manage to string together just Euclidean spaces into an example where it went to infinite and finite. But yeah. Okay, so the way I stated this theorem here, this Isbell's theorem, was just an existence theorem. It just said that if I give you a metric space, there's some mysterious hyperconvex space that it lives inside. But actually, there is a pretty concrete description or construction of this space due to dress. So let me now describe that a bit. Should have done that before. Okay, so constructing hyperconvex hulls. Okay, so we're going to construct the hyperconvex hull E of x as a subset of r to the x with the L infinity metric, where this thing is just functions from x to r, and with the sub metric. So this thing's injective for reasons that were down here, and this is going to be some subspace of that. It's going to with the subspace metric in particular. Okay, so given a metric space x, let delta of x be the set of functions such that f of x plus f of y is at least the distance from x to y for all x and y. This is just some collection of functions. And say an element of that delta set is extremal if there's nothing smaller that's also in delta. If there is no other g in delta of x such that g of x is at most f of x for all x So anything that's point-wise at most it and isn't it is outside delta. Okay. Right. Okay, and then it turns out that the hyperconvex hull is just the set of extremal functions. Okay. So
So it's basically the same as saying that that inequality is that there.
For each-
At some point.
yeah, for at each x there, yeah, okay. If it's a finite space, then it's actually realized, and otherwise it's a supremum. There's a supremum involved. But yeah, it's yeah, exactly. Yeah. Okay, so I said that there's a fairly concrete construction, and at the moment you might be thinking that I lied to you because this thing is pretty hard to imagine what's going on. So let me do an example of a metric space that has 2 points.
And sorry, and where is x inside E of x?
Oh yeah, very good question. So there's a map E which takes x to E of x, where E of x is the function distance from x to blah. So in particular, this function E of x evaluated at x is 0. Yeah. Yeah. And the only points that live in, well, okay. Yeah, that's how it lives inside. Yeah, and you can check that this thing's an isometric embedding. Yeah. Okay. So example, x is the set 0, 1. So it's just 2 points, and they're a distance 1 from each other. Okay. So here, delta. This is it's the set of functions from a 2-point thing to R. So in other words, an element of the plane. And it has to satisfy these inequalities. So it has to have f1 plus f1 is at least the distance from 0 to itself. So f1 plus f2 is at least 1. Okay, so delta is this subset of the plane. Yeah. This is 1, 0, and this is 0, 1. So you've got to have both coordinates positive, and the sum needs to be at least 1. Okay, and then E of x is the extremal things. So definitely anyone in the interior here is not extremal, because I can just come diagonally down. But also this guy over here is not extremal, because I can just move to the left. And I left one coordinate the same and decrease the other. So the extremal functions in here are just the things on this interval. So the injective hull is an interval. Okay. Okay. More generally, if I take a finite metric space, then when I want to compute E of x, I start by looking at delta of x, which is just a region of Rn, where n is the number of points, defined by a finite set of inequalities. Then delta of x is, well, okay, E of x is obtained by extremizing a finite set of inequalities of this form. Okay, so in particular, E of x is a finite polyhedral complex. And yeah, like I said, if I started with 3 points, then I would get a tripod. Once you start having 4 points, you start getting two-dimensional things sometimes. Yeah, and as it goes up, you get bigger possible things here. But yeah, it's just some finite polyhedral complex. And actually, you can be more precise about what the cells in this polyhedral complex look like. So let me make a definition. The standard n-author scheme, which sounds much fancier than it is convex hull in Rn of, okay, let me draw it first. So you've got the origin. I'll draw it at the same time, actually. The origin, and then I put 1 in the first coordinate. And then I go 90 degrees, and I put 1 in the second coordinate as well. And then I keep going. So the three-dimensional one looks like this. So this is 90 degrees. This is 90 degrees. And then I take the whole, and I get this simplex where all of the angles are 90 degrees. And the metric I'm going to put on this thing is the subspace metric from Rn with the L infinity metric. Yeah. Okay. There's an equivalent way of saying what that thing is, which is take the n-dimensional cube and then take its barycentric subdivision, and the cells you get from that are these things. Yeah, there's a two-dimensional version of that picture. I take the square, I put a point in the middle, and I put the point in each edge, and then I connect for containment. Okay, and now let me also define the n orthocone, or orthocone, is just the unbounded version of this. So rather than chopping it off at some finite level, you just let it go off to infinity. So, okay, get this. I feel like I did something weird there. Yeah. Okay, well, it's this picture, but longer.
Every segment that starts at the origin becomes
Yeah.
But the other ones don't.
The other ones don't, no. Yeah. Yeah. Yeah, instead of chopping this face off at the back, I just let it continue. Yeah. Okay, and right, so then the fact is that more than, okay, I said that the hyperconvex hull of a finite metric space is a polyhedral complex. The cells are all orthoschemes, or you can subdivide it so that the cells are all orthoschemes. The fact Okay, so you can think of orthoschemes as being kind of like the building blocks of hyperconvex spaces. In the same way that cubes are the building blocks of cube complexes, these are kind of the minimal piece. Okay, there's a difference in that this is a continuous notion. You can have things be as small as you like if you're looking at an arbitrary metric space. So orthoschemes are more analogous to cubes in median spaces rather than in cube complexes, but same kind of idea. Okay, now I will state the theorem, and then I'll stop because I'm running kind of slow. Okay, so the theorem says that let X be an n-dimensional hyperconvex space every n quasi-flat lives at finite Hausdorff distance from a finite union of orthocones.
And what is the dimension?
N.
No, I mean like what does n-dimensional mean?
Oh, sorry. Yeah, topological. Yeah, topological image. Yeah. 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 So there we go. Stop there.
Any questions?
Yeah, sorry, I butchered that a bit. It's okay. So what did I do to make the orthoscheme? I started at the origin, and I put array in the direction. I put an interval of unit length in the direction of the first basis vector. This time I'm going to take an entire line in that direction, and then I also put an interval in the direction of the 1, 1 vector. This time I'll put array, and then I did the same in the 1, 1, 1. If I take a slice through this at length 1, then I get this is the n orthoscheme. But the orthocone is this whole thing that goes off forever. Sorry, the slicing is just supposed to be to make it clearer what it is. The orthocone is just this subspace without any slicing. The orthocone is, yeah. Let me remove the slice. And that's the ortho. Yeah. Does that make more sense? Yeah, exactly. So the orthoscheme is take a square and barycentrically subdivide. Now, instead take the plane and imagine doing barycentric subdivision, but kind of at the origin. Then you get 8 of these regions. So these are analogous to the orthants that we had in the theorem about cat-zero cube complexes, which were quarter planes. These are now 8th planes, and yeah, branching at 45 degrees. And so the unbounded things you get there are the orthoschemes, orthocones. Yeah.
The boundary, do you have like a boundary in these hyperconvex spaces that you use somehow?
We don't use a boundary. There is a notion of boundary for proper hyperconvex spaces of finite dimension, but that's we're using ultra limits to, like, it's more of an asymptotic cone type argument than a boundary type argument. Yeah. There's the Horror function boundary, right?
That is an ultra limit of hyperconvex.
So so this is actually one of the questions that we set out to try and answer. The answer in general is no, it turns out, and in a way that I think is quite surprising actually. If you take sequence space, so just sequences with the L infinity submetric, that thing's injective, but none of its asymptotic cones are hyperconvex, which is weird to me at least. But it is true if you impose finite dimensionality. So if you take any hyperconvex space, any asymptotic cone that is finite dimensional will be hyperconvex. Yeah.
So you recover the results of the Katsu equivalence as the L infinity thing is.
So I think you probably can. I don't know why I'm pushing that down. It's erased. I think you probably can. It's not immediate because you have to keep track of what these, what the orthoclone, how the orthoclones are glued up. But I think you probably can do some kind of pairing where you, I mean, in 2 dimensions, if I take 2 of these, yeah, taking 2 orthocones makes an orthant. And it seems plausible to me that you can do some kind of grouping like that to recover the theorem for cube complexes. But we didn't try and do it. Yeah.
So in your initial spiral, so what about the Euclidean plane? So I guess the hyperconvex closed or injective hat must be infinite dimensional.
Oh.
Do you have a way of thinking? Is there a picture of that?
Yeah, it will be infinite dimensional, and yeah, but I don't have a really good way of how to see it. I mean, yeah, I mean, the really naive thing you can think about is just you take this picture that I had before of why it fails to be hyperconvex. If you want to take the hyperconvex hull, you can still take balls around these points, but you have to enforce that there is a point in common. So for this set of 3 balls, you will have to add some point that corresponds to them. And that point isn't in the plane because then you wouldn't be adding it if it was already there. So you're adding it sort of above, but it has to be at the correct distance from everything. So maybe you can picture that kind of creating some little 3-dimensional lump here. Then you're going to have to keep going and iterating that. And you've got this 3-dimensional lump here and a 3-dimensional lump over there and some 3-dimensional. Well, okay, yeah, the Euclidean plane isometrically embeds in its injective hull. So I can consider the balls that have these radii centered on these points. And because they intersected pairwise in the plane, they intersect pairwise in the hull because it was an isometric embedding. I'm just saying consider 3 points, x, y, and z, and balls that have radius rx, ry, and rz, so that they intersect pairwise. Now inside the hull, I have a corresponding point, e of x, e of y, e of z, and corresponding balls that have radius rx, ry, rz. They still intersect pairwise, so there is a point in common in the hull. And just the intuitive idea was supposed to be that you had to add it somewhere, and it made some more dimension, but then you iterate and it has to blow up. It's very loose. But, yeah.
If your space is already hyperconvex and you do the hyperconvex hull construction, you get the same space out, right?
You get something isometric to it, yeah.
Is there a nice way of seeing that from this definition?
So luckily Francesco was concentrating and he asked this question. So we already have a map from X to its hyperconvex hull here. And so your question is just, can we see that it's surjective? And so a point, if I take a point in X, then there is some coordinate where it gives me 0, notably namely evaluate the function distance to x at the point x, and I think that characterizes points that are actually in the space you started with. Okay, the standard way of showing that you get something isometric back doesn't use the definition of hyperconvexity that I gave. It uses the equivalent notion of injectivity related to what Jack asked. But so I don't know if there's an easy way of seeing it using the definitions that I gave. But it is true that this map will just be an actual isometry rather than just an isometric embedding. Yeah.
Why this x is just 0 is not
Yeah. Okay. This is because yeah, because I did a slightly sneaky thing when I defined hyperconvex, which was that I assumed that I started with a geodesic metric space.
so the definitions
You can define it for a general metric space, and then it implies that it is geodesic. So I can tell you maybe I'll tell you afterwards the definition for a general metric space. But instead of saying pairwise intersecting, you have to say something slightly more annoying. But yeah, the point is that this is not a geodesic metric space. So.
Complex, is it coming from some subdivision of the polyhedral complex?
Yeah, exactly. So yeah, this delta, it's defined by these. The equality set of one of those is just a hyperplane, and then so here I had 3 hyperplanes, and then you get some region, and you take the boundary of that region, and that's something formed by these hyperplanes. If you didn't have enough hyperplanes, things won't already be cut into orthoschemes. You might need to cut things up more to get orthoschemes. But yeah, it's a natural subdivision. In fact, this is living inside Rn with the L-infinity metric. Take the standard cubulation of Rn, and then barycentrically subdivide all of the cubes. You can just overlay that subdivision of Rn, and that gives you an orthoscheme subdivision of the